Board. Okay, welcome back. Hope you had a nice weekend. A little bit of rain, that kind of cooled things down a bit. I thought that was kind of nice here, at least here in San Marcos area. So let me go through the administration stuff first, and then we'll start with chapter 18. Okay, so of course we have Zoom class here until Thursday, you know, from noon to 1:40. The homework for chapters 18 and 19 is up on Tracks. If you look through it and you see a picture missing, please tell me. As of today, I'm not, sorry, not Tracks, Top Hat. As of today, I looked through it 3 times and I saved a couple things, and it looks like they're all there on my side. But if you guys could go review that, make sure that that seems to work. I only had one missing picture on one person's exam, so I think whatever I've done to fix that, it worked out really well. And nobody got locked out on the exam. So everybody seemed to be able to take the exam the first time without the same stress we had the previous one. So I think I have dialed in our exam parameters, and I think that I figured out the best way to upload pictures to the Top Hat testing. So I think everything seems to be moving smoother. If you are having issues, go ahead and email me and I'll try to solve that problem. Okay, quick question. Some classes in the semesters will be switched to online and being applied to all classes. Okay, that's a very good question. And yes, there's a significant number of classes that have been switched to online only. And there's a significant number of classes that has been switched to hybrid, which is a 50% capacity. So as we get forward, some things will be easier than others. For example, my Organic 1 class is going to be what we call 50% capacity hybrid, meaning that everybody has at least a 50% chance of coming to class once a week, and then when we test on Fridays. For my other class, Introduction Organic, I have a live version of it with in-class persons, and then I have a portion of it that's online only. So, and then I have another class that is completely online. So I get to do them all. So, it's class dependent. You might want to look at who you're registered for and ping your professor to find out how it's going to be offered. I know that I've had several people pinging me on things that I'm currently doing, including the fact that we might even have a virtual lab section available to some students who have issues. So that is something. Clay, you have your hand raised there?
Yes. How are we supposed to, so I tried to look to see what classes were going to be offered completely online.
Mm-hmm.
Has that already changed in the register for when we register for classes? And then the other question is, you know, we're only allowed to register when it's our specific time according to how many credit hours we have. How is that going to work for the re-registering? Do you know any of these?
Class changes are different than registration, so those should be handled separately. And we had to have our requests in for hybrid versus not hybrid 2 weeks ago for the expressed purpose of having it all online. I do not know if it's live yet, but you should start seeing, if you're already registered for a class, go ahead and email the professor or lecturer and ask them, you know, how is it offered? And, you know, because I've had people that want to be in the live portion and some people that want to be in the digital portion. So those are, you know, things that individual professors are trying to figure it out.
Awesome, thank you.
So none of you will be taking my class because I'm only teaching Organic 1 and Intro to Organic and Spectroscopy. So, but I plan to teach them all differently. My spectroscopy class is 100% in person, but it's only 20 people. And then I have 100% online one of my classes, and then a hybrid on one of my classes, and then 50-50 with online testing on one of my classes. So I think professors are trying to be flexible and trying to be able to, have as many live person classes as they can until, things get complicated. And then they'll have a backup for an online or a digital only version. So been doing a lot of training lately, so we'll see how that goes. Okay, does that answer questions on that right now? Okay, you have a little thumbs up reaction button on your keyboard if you want. Okay, let's back to our class in administration. So here we are at Zoom. Homework is up, and it'll be up until, of course, 11:59 on Thursday. After that, it'll be available for you to review. You get 2 chances to get it right, and then after that, it's review. It's, again, 30 questions, about 15 questions for 18, 15 questions for chapter 19. We'll have our third group project. It says second on here, but it'll be our third group project on Thursday. And it's going to be focused on cyclization, specifically the Dieckmann and the other intramolecular interactions we'll be starting to deal with. They're a little hard to get your head around, but once you practice it a little bit and start counting carbons, that's what the exercise is for, to make sure you're counting the carbons and figuring out what the end products are. And so that's what and that actually sums together all of chapter 18 and 19 quite nicely together in that little activity. So I highly recommend, if you can come, please do. If you can't, go ahead, download it and upload it after you've completed it. Our third exam will be over the 18 and 19. It'll be, again, 30 questions, multiple choice. I'm going to not change any of the parameters we did on last Friday, so because that seemed to work. And then we will have everything kind of set for our last 2 chapters at the beginning of next week, and then we'll have study time to prep for our final. Okay, again, our Zoom meeting changed for this week. I see well, at least some of you, 36 of you, have figured it out. And so if not, come back here tomorrow and we'll do it again. Okay, so again, I've started recording. I'll record the rest of the lecture and I'll host it as soon as I can. And we will hopefully have them all up sometime today. I do have some training, so it might be a little later. It might be after 3. So I'm doing online digital training to do better presentations online. So you'll, that's what it is so far. Okay, so what I'd like to do now is go ahead and share my screen. Let's see, I think we're all on the same Wi-Fi now. There we go, all right. So, and I'm gonna move this screen up here. Again, I do it in the grid view up here, so I can look for response, thumbs up or questions. So, but just go ahead and chime in if you need to, because some of the things we're going to talk about might get a little complicated, and that's okay. Just go ahead and chime in. We have a pretty good set of slides here today, but we want to make sure everybody has an opportunity to understand. Okay, so let's talk about chapter 18. Chapter 18 is about a follow-on to the last 2 chapters we talked about with the carbonyl compounds, okay? So we started with carbonyls, with the aldehydes and ketones, and we saw that they had a certain kind of reactivity and they changed certain properties. They had dipole-dipole interactions. And then we saw that they mainly did addition reactions with that carbonyl because there was no good leaving group. There's no stable anion, no weak base, okay? Then we moved into the carboxylic acid derivatives, and here we've changed out a hydrogen or carbon for some other electrophilic atom like oxygen or nitrogen or chlorine, and we saw that we could get substitution reactions happening on those, okay? So we weren't just limited to that addition product or that substitute. We gained that substitution product. Okay, So, and it all happened because of the partially positive carbon of the carbonyl and some things about resonance and resonance stability, okay? We're gonna extend on that theme, but we're gonna do it on the carbon next to the carbon with the carbonyl, okay? So, and what we do is we call those carbons that are next to the carbon with the carbonyl the alpha carbons, and it is not sharing. Let me unshare and reshare here. New share. There we go. All right. So up to now, we have been doing this reaction where, you know, we're working with the carbonyl is the thing we were attacking with our nucleophiles, and we were generating, you know, our tetrahedral intermediates. And sometimes if we could spit out a good leaving group, we'd get substitution reactions. Okay. So now we're going to deal with the carbon next to the carbonyl. Okay. And how the carbonyl influences the reactions at that site. Okay. So this is what we call the alpha carbon. It's the carbon one over from the carbonyl. And the hydrogens on that carbon are called alpha hydrogens, okay? So this is a very key phrase. The alpha carbon is the first carbon attached to the carbonyl, and hydrogens on that carbon are called alpha hydrogens. And those are the ones, the hydrogens, we're gonna have to really focus in on and figure out what we're gonna be doing with those to create new nucleophiles. Okay, so in the case of this right here, we have a base coming in, removing one of those protons, generating an anion at that alpha carbon here, and that's our new nucleophile. That's our new attacking species, okay? So we haven't used this one up to now, so this is our new nucleophile to play with. Okay, so why can we do this, okay? So let's talk again about the basicity or the acidity of these hydrogens on carbon, okay? The carbon and hydrogen, it's a fairly nonpolar bond. They're very small electronegativity difference. And if we just had a long chain alkane, we would call those protons our weakest acid we really deal with here, okay? They have a pK of 60, which makes it our weakest acid of anything we've really worked with up to now, okay? However, by having that carbonyl adjacent to that carbon, we can lower the pKa, and by lowering the pKa, we are raising the acidity, and we can pull it off more easily with weaker bases. If we can pull that off with a weak base and generate an anion, that anion can then do additional chemistry by attacking other things. And so what we're going to see here is by looking at the number and nature of the carbonyl compounds at that carbon, we can change the acidity of those protons, okay? So that's part of the reason it helps change the acidity of that proton. But the other thing that helps us is the fact that we have resonance stabilization, okay? If we just pulled off our hydrogen here because of inductive effects of the carbonyl here, that does part of the job of making it acidic. The second half of the job being done to help it be acidic is the idea that we can now stabilize this anion just by moving electrons in and moving electrons up. And we have part of our negative charge stabilized by the oxygen and part of our negative charge stabilized by the carbon. Remember, oxygen is more electronegative than carbon, so if we can stabilize that negative charge on oxygen at least part of the time, it makes it easier to do. Just like in the case of our acetate ion, that's an acidic proton because the anion is stabilized on oxygen atoms. Okay, so like I said before, we can change the acidity of these alpha hydrogens by having things next to them that can make that more stable anion or a more delocalized anion, okay? So we're looking for two effects, an inductive effect and a resonance effect. So in the case of our first one here, and I'm gonna blow this up a little bit on this first side here, our weakest or least acidic compound we're going to be using in this chapter is what we call is the amide right here. And so if we look at that, we have a carbonyl here, and that's giving us that inductive effect and that resonance effect with that oxygen here. But we have a nitrogen here, and the nitrogen is more electronegative than carbon, and therefore has a little more electron density to it than a carbon would. Okay, so if we look at our two weakest, least acidic adjacent hydrogen, alpha hydrogens here, they are compounds that have a carbonyl and a nitrogen bonded to it, or in this case here, it's the carbon-nitrogen triple bond. Okay, so those give some amount of electron withdrawing, but it doesn't do a whole bunch to help stabilize that anion there. The next most acidic alpha hydrogens we have are those that are adjacent to an ester. Okay, so we have the carbonyl and the oxygen here helping stabilize that anion, but we also have an electron donating group directly attached to the carbonyl. Okay, that electron donation by that oxygen decreases the amount of electrons the carbonyl can pull away from these alpha hydrogens. Therefore, while it can deprotonate those, it's not helping make them acidic. Okay, so what you should start seeing is the effect of this electron donating group on the other side of the carbonyl compound and how it affects the acidity of those alpha hydrogens. Okay, by taking away this electron donating oxygen and putting a carbon here, that is basically a nonpolar bond. Therefore, there's no inductive effect on there. And then this would be considered our most electronically neutral alpha hydrogens. Okay, they are only affected by the stabilization of that oxygen and the electron withdrawing capability of that carbonyl. Okay, so you might want to use this as your baseline, saying, okay, carbonyl is basically doing all the work. That methyl group on there is not doing any more of the group. And so this is what I would consider our baseline for acidity of those alpha hydrogens, just because of the carbonyl. As you add donating groups to it, the acidity goes down. The pKa goes up, but the acidity goes down. It takes a stronger and stronger base to remove those protons. Okay. Now, if we look at an aldehyde, again, hydrogen is just slightly more electronegative than the carbon is, and therefore we see a slight increase in acidity, okay? Lower number and an increase in acidity. So we're starting to pull electron density away from the carbonyl, and by pulling electron density away from the carbonyl, it can pull more electron density from the other side, making those alpha hydrogens more acidic. Okay, so that's going to be the common theme we see on this side right here. So what we've done is we have our alpha hydrogens here, and we have now two carbonyls on that system. Okay, so now it can pull in either direction or both directions at the same time, and we can stabilize our anion on either of those oxygens. However, we do have electron donating groups here. So while it is more acidic than having a hydrogen there, by doubling the effect of having two carbonyls, it should be greatly affecting the acidity of that proton. And we do see it increase, but we have some electron donation. Okay, if we add two cyano groups on here, remember those are kind of like protected carboxylic acid derivatives, we can increase the acidity again. And by removing one of the oxygens on one side and replacing it with carbon, our acidity increases again. And then by removing the last of the donating groups, that oxygen on the ester group here, giving us a diketone compound, that is one of the more acidic systems we will see in our formations of these alpha hydrogens, or these ions we're going to be making out of these. Okay, so the key takeaway for this is that the more delocalization you can have with the anion formed, i.e. more oxygens to put it over or more atoms to spread it out over, the more acidic it becomes. The more acidic it becomes, it means you can use a weaker and weaker base. Therefore, it is more reactive. Okay, so that's the key of these, is always looking about how much of the delocalization we can get, and where it can pull electron density away from those alpha hydrogens. All right, any questions on that? Okay, so I'm going to move on to our next thing. The next thing I want to talk about is what we call a keto-Enol tautomers. Okay, so a tautomer is basically going through two different possible structures. These are not resonance structures because we're moving a hydrogen. Okay, so that's the key here, is that resonance structures only move electrons. Tautomers, you actually can move a hydrogen and have that hydrogen moving back and forth. Okay, so we want to make sure that we don't confuse the two because they are very different. So in the case of the Enol keto tautomer, we saw that we had this, oh, where's my errors? I think we saw that we could make a resonance hybrid of our ketone, saying that there is a partially positive charge on that carbon and a partially negative charge on that oxygen. And that was the major contributor to the reactivity of our ketone, or our carbonyl compound here. Okay, now if we extend that conjugation and want to say, oh, well, we can have a partially negative charge on our oxygen and a partially negative charge on our carbon here, okay, we can then move that hydrogen back and forth between two locations and have two stable contributors here. So in the case of the keto contributor, it's the one that looks like a ketone, okay? So we have our carbonyl compound and it's bonded to two carbons here, and what we have our sp3 hybridized carbon alpha carbon, okay? So if we were to deprotonate that, move the electrons in, and then move the electrons out to the oxygen here, and have that hydrogen protonate that oxygen in here, this is what we call the Enol tautomer, okay? En for the fact that you have a carbon-carbon double bond, and all because you have an alcohol. Remember last semester when we talked about naming alcohols with alkenes in them, we called them enols, okay? So this is the same thing, it's just the other tautomer of the ketone. We've moved the proton from the alpha carbon to the carbonyl oxygen. And it can move back and forth, back and forth, back and forth. And like all of these reactions in equilibrium, there's typically a more stable form. Most of the time, the ketone form is the more stable form. That's why we look at them and say, oh, it's the ketone, it's not a enol. Okay, so almost always they are more stable. And this has everything to do with the idea that the carbon-oxygen bond is actually stronger than the carbon-carbon double bond. The carbon-oxygen double bond is stronger than the carbon-carbon double bond, and partially because it's polarized. Okay. So how can we use this to our advantage? Well, the cool thing is that we don't have to have a lot of it at any one time. So we can actually make it go through this enol keto tautomerization with either acid or base. Okay, so in the case of acid mediated tautomerization, all we have to do is protonate the carbonyl oxygen first. And then when it protonates the carbonyl oxygen, that means it's going to make it easier for that hydrogen to be pulled off of the other side. And let me blow this up here. So the idea is that if we take one of these lone pairs from this oxygen over here and have it reach out and grab one of the hydrogens and protonate that species, we now have a positive charge on the oxygen here. And therefore, these electrons can kick in and our electrons can come up here to give all of our atoms an octet and have no charge at all. Okay, so in this enol form where the oxygen is protonated, it is changed hybridization of the alpha carbon. Okay, we went from an sp3 hybridized carbon here. That didn't, okay, sp3 hybridized carbon here, which is tetrahedral, to an sp2 hybridized carbon here, which is trigonal planar. Okay, this is important because if you can go through this enol intermediate, that means you will lose stereochemistry at that alpha carbon. Okay, so we're gonna look at that in more detail later, but I wanted to show you why it's losing it, because let's say you have it in the S form here, and you go through the intermediate and it gets to the enol. And again, this is a completely reversible reaction. When it goes back, there's no preference for that hydrogen to come on either side of that double bond. Therefore, it will come back equal portions on one side versus the other, and you'll end up getting a mixture of R and S in your system. So you're going to mix up your chirality because of this. Okay. So if the acid-mediated tautomerization has everything to do with the oxygen being protonated first, that means the base mediated system is going to have something about pulling the proton off first, okay? And as we see in our mechanism down here, we see that a base can come in and tug on that hydrogen on that alpha carbon. Okay, now remember, we've already increased the acidity of that hydrogen by having that electronic drawing group nearby. And now we've also increased it by the idea that we can actually have this resonance stabilization. So in this case, our hydrogen goes away, and the electrons that were in that sigma bond get kicked in to give us our carbon-carbon double bond, and then our anion of our oxygen here, which now acts as the base and can give us our protonated intermediate here, our enol, and again, regenerate our basic species. Okay. So, and again, each of these steps is completely reversible, but it still goes through that sp2 to sp3 hybridization change and sp3 to sp2 hybridization change back and forth. Okay. Now, we know we can do it with acid, we know we can do it with base, but where does that equilibrium really lie, okay? So one of the things we want to think about on this is that in the case of something like acetone here, okay, even in the presence of acid or base, still 99.999% of the time, it's going to be in the ketone form, okay? So it's going to act like a ketone. However, in that 0.001% of the time that it's the enol, it can react as an alkene and or an alcohol, okay? So what you're seeing here is that in the case where we have really, you know, these two positions are not help contribute to the acidity or basicity of those alpha hydrogens, you're going to see most of the time the ketone is found, okay? However, if you influence the system such that you have two electronic drawing groups on that same alpha carbon here, you can actually, number one, increase the acidity. Number two, you're going to see that you'll find the enol is actually the more stable form. And in this particular reason, it's more stable because, number one, you have two of the carbonyls increasing the acidity of that alpha hydrogen. And number two, you can form a six-membered hydrogen bonded ring. Okay, the fact that you can actually form this six-membered ring here in that hydrogen bonded form, that it is driving its stability. So in this case, for this beta dicarbonyl compound, this beta diketone compound, it actually is more stable in the enol than in the diketone compound. And we see that its reactivity will be different because of this, okay? Now, there's another thing that drives this enol keto tautomerization. And in this case, it was the formation of a hydrogen bonded six-membered ring. But in the case of phenol, we're actually driving it to the enol form because of aromaticity, okay? All right, so in the case of this first structure here, right here, you would think, oh, look, it's a conjugated ketone. It should be the more stable form. However, if you turn it into the enol form here, you actually now have those electrons in the aromatic ring and are contributing to the aromatic stability, and therefore you have 99.99% of it being the enol form and very, very little of it being the keto form. Okay, so transitioning from the enol to the keto is the key phrase we're doing here. And the ability to form that intermediate will shift that equilibrium from one to the other, and based on, and then you can also use aromaticity as a driving force to shift it to one form or the other. Okay, questions on that? Okay, and we're doing good on time. All right, so let's see how we can use